Our project is a virtual reality learning environment with real-time brain signal monitoring, and this is our final presentation. I'm Jacob Mitchell.
I'm Zane Frabit.
I'm Brendan Jenkins.
I'm Yumna Rizvi.
And I'm Ethan. Over the past year, our senior design group built a virtual reality learning environment. In our environment, we use the brain signals that are obtained from Emotive's Epoch Plus and EEG brainware device to provide real-time monitoring of the user's physiological state. Within the module, the user is given the ability to interact with models by using the Leap Motion Controller, which is a small but accurate hand tracking device. The modules are intended to be a teaching aid, bringing to life many lessons that are just hard to teach through an online class. Our project helps educators and students gain greater insight on the students' capabilities during and after a lesson. This allows educators to fine-tune their lessons for each student. With that, educators can also bridge the gap between online learning versus traditional learning by viewing the students' activity as they work. The problem that our project stemmed from is the COVID-19 pandemic. With COVID-19, as you all know, social distancing was required globally. This greatly impacted the way public schools and universities functioned. All educational systems had to adapt. A majority of students were forced to stay home and learn through their own computer. This came with many faults, including giving students a great sense of freedom and responsibility that they never had before, decreasing the engagement and increasing the workload of the student. On top of that, students face external distractions that being in class never had, like family stepping in. Educators also faced hardships as they had to modify all their lessons to become virtual. Not only that, it's hard for everyone to interact online. There's no face-to-face option where students can meet other students and engage in friendships, or for educators to visualize how a student is doing in class. Our project aims to solve that by providing a virtual environment, seen in Figure 2, that both students and educators can use. It expands the learning capabilities that are limited through only online learning. Our project also sets an opportunity for students and educators to interact with each other. Along with that, our project will provide real-time monitoring of brain signals for both the educator and the student's use. From the Motive Pro software, our project is also able to share the performance of a student based off their brain signals. These metrics can be used for various things like personalizing lessons and giving feedback. And with it being real-time monitoring, the lessons can be adjusted as needed whenever. So why did we choose virtual reality? Virtual reality allows us to bring visualization of materials. This, in combination with our repetitive learning materials in the modules, will help combat the low rates of engagement seen in online learning. As can be seen in Figure 3, a study of engagement scores with traditional classes versus VR classes from the Journal of Biosensors and Bioelectronics show that VR classes bring the engagement scores of students to nearly as high as traditional classes. Virtual reality also provides a safe and hands-on environment for many things like labs and studios that have the potential to be dangerous.
Our project leverages virtual reality to provide students with learning insights using EEG data from brain signals. It helps bridge the gap between teachers and students in online or marginalized environments where interaction is compromised. This tool helps educators improve their method of lesson delivery and helps students tailor their learning strategies to be as efficient as possible. Our project is designed to collect brain signal data using the emotive headband for inputs to achieve an educational virtual reality environment. This project uses the VR headset such as the Mirror Tab and a Leap Motion Controller to allow hand movement and control environmental interactions. The emotive headset monitors specific points on the head and provides the raw brain signal values from the user to be displayed in a format that allows for teacher interpretation in real time. The computer accepts an input using the brain signal data while providing power and accepting inputs from other components such as the controller and VR headset. The computer uses the output and results into the VR environment. Our project uses the captured raw EEG data, which is acquired by the emotive device using 14 sensors. There are also 2 ground reference points to which the voltage of all other sensors are compared to. We analyze these EEG signals to extract the engagement and emotion of a student for insight on their emotional and learning process. The highest frequency range amongst the brain signal waves ranges above 30 Hz and is called gamma waves. They are functional during attention and memory relevant tasks. Gamma wave incrementation occurs during object recognition activity, which is part of selective attention. The frequency that ranges from 12 to 30 Hz is called beta waves. Beta waves show fast and small focused concentration. Beta and gamma waves are related to attention, perception, and cognition and are the main interest to us in education. We also have alpha waves that are seen when the person is in a relaxation state and theta waves for emotional stress such as frustration and disappointment. Lastly, delta waves occur in sleep and dream state. Using this information, we can classify when a student is retaining information. These are some important equations that are used by an important feature in VR, which is the head tracking in 3D space. Our emotive headset will output quaternions Q0 to Q3 calculated from accelerometer, gyroscope, and magnetometer data. Using these quaternions, we can use the equations in Figure 6 to calculate Euler angles, pitch, roll, and yaw respectively. Using the rotation matrix shown in Figure 7, we are able to feed our pitch, roll, and yaw into these equations to calculate exactly where the user will be turning in 3D space. The 14 scalp sensors or channels are high-pass filtered to remove the DC offset from the data. They are then pre-amplified and low-pass filtered at an 83 Hz cutoff frequency. The analog signals are then digitized and filtered using a fifth-order sync-match filter. They are low-pass filtered and downsampled for a sampling rate of 128 Hz frequency.
To build our virtual classroom, there were a couple of things that we needed to implement. First, we decided to build learning modules inside of Unity. We built the main structure for almost everything in the games, besides the SDKs, and we also built C# scripts. We also implemented the Leap Motion LiDAR camera for interaction with the environment, and we used the emotive headset to get data for performance metrics as well as camera motion throughout the environment. We also have a teacher hub that is linked to our students view, which allows the teacher to monitor multiple Unity instances at one time, and the teacher can obtain performance metric data from the students that allows them to monitor how their students are performing. This performance metric data will be saved and loaded offline for access at a later point in time. Project architecture. This is a level 1 diagram for our project. As you can see, the user inputs and external distractions get input into the system. The user inputs data into the Epoch Plus and the Leap Motion. From the Epoch Plus, there's EEG data, which gets turned into performance metrics and output to the game engine, as well as motion data that's used to control the camera. All of this is put into the student view and accessible by the teacher. Software functionality. This is the camera movement data path. The student subscribes to the motion data from the Epoch, and these are turned in, or the quaternion values from there are turned into Unity quaternions through Euler angle mapping. This is then used to transform the camera rotation in the scene. For cube interaction, an event manager on the teacher side can be used to increase or decrease the speed. This is sent over a network connection and put into the settings menu. The student also has a slider on the back of their left hand, which allows them to control the speed of the blocks inside of the learning module. From there, the box movement is directly affected, where it will either be destroyed over time, or a raycast interaction with the Leap Motion hand objects will cause the value to be added to the equation. The input from the equation is then put into the game manager. If the value that is put into the equation ends up being less than the answer that you're looking for, the game will pull for the next value. If the value is equal to the number that the game is looking for, then the completed and the correct values will both increment, restarting the module. If the value is above the value that you're looking for, then an incorrect message will be shown, incrementing just the completed section, restarting the scene until the desired number of scenes have been completed. For the teacher hub, the student has their EEG data read from the Emotive Plus and sent, or the Epoch Plus, and sent into the performance metrics. These performance metrics are then passed over the network and sent to the teacher, where the teacher can view the entire class at one time. These data points are also saved in a CSV file that can be accessed at a later point in time.
Okay, so this is our testing approach. We had 4 major components within our project that we knew we needed major testing in order for our game to work fluently. These tests consisted of head tracking, performance metrics, gameplay testing, and teacher hub testing, which we all will respectively talk about throughout this presentation. So the first major test we did was head tracking. This consisted of using our background knowledge of quaternions and rotation matrices to be able to do head tracking within Unity. During the testing, we were able to identify issues such as gimbal lock and develop solutions throughout the testing using Unity scripting API. A large component of this testing was getting a smooth, low latency data stream from our created Cortex application to send quaternion data into Unity for manipulation. Shown in 14 to the figure 14 to the right is our experimental apparatus, obviously with the headset being on the user's head, with the Emotive Pro software in the background. So we decided to use MATLAB for our validation because MATLAB's ability to be able to handle quaternions. In our validation testing, we were ideally comparing our theoretical angles to our actual measured angles to ensure processing and handling processing and handling the data correctly. Excuse me. In conclusion, these tests were successful, and in terms of criteria for completion, we still have some gimbal lock issues, but for our game's application, we were able to get the head rotation to work correctly. Next was the next test was our performance metrics testing, which was actually pretty straightforward. There were a total of 6 performance metrics that we which are stress, engagement, interest, excitement, focus, and relaxation. This testing helped us scale our data to a more readable values for the teacher. And shown in figure 16 to the right, we have an example of us testing the performance metric in the Emotive Pro software. And that led to our validation. So basically, we decided to do our validation test for our performance metrics. For example, deep breathing was shown to increase relaxation levels and reduce stress. So what we would do is we would go in the Emotive Pro software and we would test to see that if we did deep breathing, that our stress levels went down and our relaxation levels went up. And that's kind of how we did validation for every single performance metrics throughout. Another test was to now incorporate our learning module we created in combination with the performance metrics, the controller, and the head tracking. In figure 18 to the right, obviously we have our controller hands in there, but we'll show later on in a video the head tracking as well as the performance metrics working in conjunction with our game. But in this test, we were basically, fixing any compiler errors that occurred during the combination of all these components. And testing was used to find and develop solutions to help fix them.
The last major component of our testing was the Teacher Hub. There's no actual numerical data for this test, and all we're doing is sending the information back and forth from the student to the teacher. You can see that for our first test, when we're sending arbitrary values, the values are increasing from 0.1 to 0.6. These are actually set on the student side, and this is actually the Teacher Hub. The second test that we have is sending the actual performance metrics in real time. This is seen in the video. The conclusion of this test was that it was very, very good, and the correct values were sent over the network very quickly, but it did take quite a bit of trial and error using multiple different networking protocols, such as UNet and Photon. Here's a video. We decided to speed it up a little bit so that it wasn't taking a large portion of our recording. Here you can see that he's looking around. The motion data is pretty accurate. You can look to the left, look to the right. You can see that the hands pop up correctly on the screen. You can also see that he can play the game. He can reach out and grab different values, adding plus, subtracting from it, based on whether it's a plus or minus. Here is our Teacher Hub showing correct values of the performance metrics. You can see that as we increase the speed on the teacher's side and decrease the speed on the teacher's side, the students' boxes speed up and slow down respectively. You can also see that as we look at the values can change in real time, and also they are accurate to the sliders. This is our full game working. The bottom right is the teacher menu. The top right is the actual student view, and on the bottom left we have a video of an actual person playing it with the full headset on. You can see that the performance metrics started at 0 but do update. Now for the fun spent. Without the Epoch Plus, which is provided to us by our SAT faculty supervisor, and not including the Emotive Pro software subscription, the cost of the project is approximately $141.86. Including the Epoch, this price goes up to $991.86. The Emotive Pro also has a recurring monthly fee of $30. Incorporating the roughly 1150 hours spent on the project, that would come out to about $33 an hour, which is the national average of entry-level electrical and computer engineers. Lastly, for the lessons learned. The important lessons that we learned are the interpretation of brain signals to allow us to actually, have a good impact on the teachers. The team working over a virtual environment, which was forced on us due to COVID. JavaScript and C# programming languages, both of which were used very intensively for Unity. Information validation to allow us to actually give our data more backing and meaning, and the usage of application programming interfaces such as ML which we use for networking, the Leap Motion, which we use for hand tracking, and the Emotive, which we use for all of our brain signals. This concludes our ECE 493 final presentation. We believe that our project is the first step in creating an immersive virtual learning environment that is on par with in-person classrooms.